Now we will continue chapter 13 on the controllability and observability of linear systems. Due to the close parallels between discrete time and continuous time systems regarding controllability and observability, in the rest of this chapter we will be able to handle both types of systems in a unified way. In definition 13.23, we start this by distinguishing between single input, single output and multi-input, multi-output systems. So a continuous time or discrete time system in state space representation, as it was defined earlier in this chapter, is called a single input, single output or SISO system if its input and output vectors are scalars, meaning that m, which was defined as the number of inputs, is equal to 1, and p, which was defined as the number of outputs, is also equal to 1. On the other hand, it's called a multi-input, multi-output or MIMO system if m is greater than 1 and p is greater than 1. It goes without saying that we could also have a single input, multi-output or SIMO system or a multi-input, single output MISO system. Then we consider a continuous time or discrete time LTI SISO system with the throughput matrix D being equal to 0. The transfer function of this system, which was defined in chapter 9, so g of s in the continuous time case or g of z in the discrete time case, is a scalar function that maps from the set of complex numbers into the set of complex numbers, and which can be written as a rational function of order n, which means that in either case, the denominator of the transfer function is a polynomial of degree n, and we call the scalar coefficients of this polynomial alpha n minus 1, alpha n minus 2, and so on down to alpha 0. And the numerator in either case is again a polynomial of degree at most n minus 1, and we call the coefficients of this polynomial beta n minus 1, beta n minus 2 down to beta 0. Recall that the coefficients alpha n minus 1 down to alpha 0 are in fact the coefficients of the characteristic polynomial of the matrix A. On this slide, we introduce a special type of state space realization called the controllable canonical form. To understand the meaning of this, first recall that in theorems 9.13 and 9.26 in chapter 9, we have obtained formulas to get from a state space model, meaning the matrices A, B, C, and D, to a corresponding transfer function of the system, g of s, in the continuous time case or g of z in the discrete time case. And in fact, these formulas hold for the MIMO case. Now, the purpose of theorem 13.25 is to do the opposite. So we are given a transfer function and we want to find a corresponding state space model, meaning matrices A, B, C, and D. When doing this, we have to acknowledge two things. First of all, going from a transfer function to a state space model only works for the single input, single output case. And second of all, the state space model that corresponds to a transfer function is not unique. So what theorem 13.25 is doing is that it's translating a continuous time or discrete time LTI SISO system given by its transfer function in equation 42 into a state space realization, which A fully represents the input-output behavior of the system, and B is canonically observable. Here, the term canonically, in case you haven't heard it before, stands for reliably or always. Now, let's take a closer look at the particular state space realization in equation 43, The system matrix, which we call AC, looks like this. So in the upper part, it has all zeros except for ones on the superdiagonal. And in the last row, it has the coefficients of the denominator of the transfer function with a minus sign, and in the order from minus alpha 0 up to minus alpha n minus 1. The input matrix, which we call BC, has a bunch of zeros on top, and the last entry is a 1. And the output matrix, which we call CC, contains all the coefficients of the numerator of the transfer function as elements, where we start with beta 0 and end up with beta n minus 1. Now for the proof of Theorem 13.25, beginning with part A, where we have to show that the state space representation in equation 43 corresponds to the transfer function in equation 42. And the proof of this is basically very simple. All we need to do is to apply the formulas from Theorem 9.13 or 9.26, namely C times in brackets Si minus A inverse times B, and substituting the particular A, B, and C matrices from equation 43 leads to the transfer function as given in equation 42. Then, for part B, we have to show that the state space model in equation 43 is controllable. And to do this, we compute the controllability matrix that we call PC for the pair AC-BC, which leads to a matrix that looks like this, having all ones on its diagonal, all zeros in its upper left triangle, and some values in its lower right triangle that are indicated with a star. Note, however, that no matter the entries in the places with a star, this matrix will always have rank n, and therefore the system is controllable. As stated in definition 13.26, a state space representation in the form of equation 43 is said to be in controllable canonical form. And clearly, the term explains itself, as we have just shown that any state space representation in this form is canonically controllable. Similarly, there also exists an observable canonical form, as stated in Theorem 13.27, where again we consider a continuous time or discrete time LTI isosystem given by its transfer function in equation 42. Then this transfer function can be translated into a different state space realization given by the system matrix AO like this, the input matrix BO like this, and the output matrix CO like this, such that A, this state space model in equation 44, is equivalent to the system defined by the transfer function in equation 42, and B, the state space model given in equation 44 is canonically observable. And the proof of Theorem 13.27 is very much similar to that of Theorem 13.25. For part A, we just verify that C times in brackets Si minus A inverse B is equal to the transfer function that's given in equation 42. And for part B, where we need to show that the state space model in equation 44 is canonically observable, we just compute the observability matrix QO for the pair COAO, which looks like this, where we have all ones on the diagonal, only zeros in the upper right triangular part, and some non-zero entries in the lower left triangular part. Observe that no matter what these non-zero entries are, the rank of the matrix QO will always be equal to n, and hence the system will always be observable. And since the state space model in equation 44 is always observable, as we have just shown, it is also said to be in observable canonical form according to definition 13.28. Our next result in Lemma 13.29 is that for any continuous time or discrete time LTI system, the controllability and observability are always preserved under any similarity transformation. In particular, recall that for any non-singular transformation matrix T, the system matrix, the input matrix, and the output matrix of the similarity transformed system are defined as A tilde is equal to T inverse AT, B tilde is equal to T inverse times B, and C tilde is equal to C times T. More specifically, the lemma states that the pair AB is controllable if and only if the pair A tilde B tilde is controllable, and the pair CA is observable if and only if the pair C tilde A tilde is observable. In the lemma, this is expressed by two facts. A, if P is the controllability matrix of the original system, and P tilde is the controllability matrix of the similarity transform, then the rank of P tilde is equal to the rank of P. And similarly B, if Q is the observability matrix of the original system, and Q tilde is the observability matrix of the similarity transform, then the nullity of Q tilde is equal to the nullity of Q. Next, we will see how a change of basis caused by an appropriate similarity transformation allows us to decompose the state space into a set of controllable states and a set of uncontrollable states, or into a set of observable states and a set of unobservable states. So consider a discrete time linear time invariant system whose controllable subspace, also known as its reachable subspace by fact 13.3, is denoted with SC, and which is a subspace of the state space Rn. The case of a continuous time system is completely analogous and therefore omitted, and will only look at the discrete time case. Recall that any vector in the controllable subspace can be reached with the system state within n steps, starting from the origin and by selecting appropriate control inputs u of 0, u of 1, and so on up to u of n minus 1. Moreover, the controllable subspace corresponds to the range space of the controllability matrix P, as we can see from the proof of Theorem 13.7. So we can write SC is equal to the range space of P. Now let the vectors B1, B2, and so on up to Bi be an orthonormal basis for the subspace SC, where I is equal to the rank of the controllability matrix. Of course, I is some integral number between 0 and n. Then we can extend this basis by additional basis vectors bi plus 1, bi plus 2, and so on up to bn, for example, by using the Gram-Schmidt procedure. So in summary, we have that the controllable subspace SC is equal to the span of the orthonormal vectors b1 through bi, and its orthogonal complement SC perpendicular is equal to the span of the remaining orthonormal basis vectors bi plus 1 through bn. Of course, we have that the controllable subspace SC and its orthogonal complement SC perp form a direct sum decomposition of the state space Rn. Based on this, we can now derive what we call the controllability decomposition. In the first step, we define the similarity transformation that is given by the transformation matrix that contains the basis vectors b1 through pn as its columns. And this similarity transformation leads to an equivalent system with the state that we call x tilde, and which is defined as T inverse times x according to definition 12.1 of the similarity transformation. And this equivalent system we call the controllability decomposition. And we let A tilde, B tilde, C tilde, and D tilde denote the corresponding transformed state space matrices. Moreover, we define SC tilde as the transformation of the controllable subspace SC, and in fact SC tilde represents the controllable subspace of the transformed system. In fact, it can be expressed by this formula, which is easy to show by the definition of the controllable subspace being the range space of the controllability matrix for the original system and for the transformed system, which by the definition of the range space can be written as the set of vectors PV, where V is any vector, for the original system, and a set of vectors P tilde V, where V is any vector, for the transformed system. And now with the formula that P tilde is equal to T inverse times P, which can easily be verified by just substituting the transformed state space matrices A tilde and B tilde, we obtain that as C tilde is equal to the set of T inverse times P times V for all vectors V. And so the result follows immediately by comparing these two formulas. Lemma 13.31 states that A, the controllable subspace SC, is A invariant, meaning that for any x in the controllable subspace, we have that also AX is in the controllable subspace. And B, the controllable subspace SC tilde is A tilde invariant, meaning that for any x tilde in SC tilde, we have that A tilde x tilde is also in SC tilde. For the proof of Lemma 13.31, part A will be on exercise sheet 14, and for part B, we use the formula for SC tilde that we have derived earlier. Now we pick any point x tilde in SC tilde, which means that T inverse x tilde is an element of SC by the above formula. Given that this holds, we have that A T inverse times x tilde is an element of SC by part A of this lemma, and hence T inverse x tilde is an element of SC tilde, again by the above formula. With the observation that T inverse is the definition of A tilde, our proof is complete. In corollary 13.32, we partition the matrix A tilde into 4 blocks, such that A tilde 1,1 is an I by I matrix, and A tilde 2,2 is an n minus I by n minus I matrix, and A tilde 1,2 and A tilde 2,1 have corresponding dimensions. Then it follows that the matrix A tilde 2,1 has to be the zero matrix. This can easily be seen because by the definition of T, which is a change of basis, the subspace SC tilde looks like this, meaning that it consists of vectors of this type, where only the first I entries take on some non-zero values, and the remaining n minus I entries are all zero. Hence, the result follows immediately with the use of lemma 13.31b. And similarly, the input matrix B tilde can be partitioned into b tilde 1 and b tilde 2, where corresponding to the partitions above, b tilde 1 is an I by m dimensional matrix and b tilde 2 is an n minus I by m dimensional matrix. Then b tilde 2 will be 0. Without providing a detailed and rigorous proof of this corollary, it's clear why this must be true, and that's because the subspace SC perp, which is associated with the states of b2 tilde, is completely uncontrollable. So, in summary, the controllability decomposition can be written as the state space model shown here, where the submatrix A tilde 2 1 is equal to 0 and B tilde 2 is equal to 0, and we have decomposed the state into a controllable part xc tilde and an uncontrollable part xuc tilde. And apart from that, we have the same input-output behavior as the original system, and the transformed state x tilde has the usual relationship with the original state x, namely by x tilde is equal to t inverse times x. Observe here that the uncontrollable states form an independent autonomous system. The eigenvalues of A tilde satisfy that they are the same as the eigenvalues of the original system, and moreover, they can be split into the eigenvalues of the submatrix A tilde 1 1 and the eigenvalues of the submatrix A tilde 2 2, where the first are referred to as the so-called controllable modes, and the latter are referred to as the so-called uncontrollable modes. The danger here is, of course, that an eigenvalue of the submatrix A tilde 2 2 is unstable, because then the state may blow up over time without the possibility to control this in any way. Depending on the observability of the pair C tilde 2 and A tilde 2 2, this blow up in the state may or may not be reflected in the outputs y of the system. Now we get to a very important lemma in 13.34 called the Hautus lemma. The Hautus lemma provides an additional condition to check the controllability or the observability of a system apart from using the controllability matrix or the observability matrix. In fact, for controllability in part A, it states that the pair AB is controllable if and only if the rank of this matrix is equal to n, where the first n columns of the matrix consist of lambda I minus A, and the next m columns consist of the columns of B, and this rank condition must hold for all eigenvalues lambda of the matrix A. For the observability in part B, it states that the pair CA is observable if and only if the rank of this matrix is equal to n, where the first n columns of this matrix are made up by lambda I minus A, and the next p columns are made up by the matrix C, and this rank condition must hold for all eigenvalues lambda of A. Now, a few remarks about the Hautus lemma before we get to the proof. First, recall from chapter 7 that the rank of the matrix lambda I minus A is equal to n anyways for all lambda which are not eigenvalues of the matrix A. Hence, the Hautus lemma could be stated equivalently by replacing lambda in the spectrum of A with lambda in C, because the rank of this submatrix lambda I minus A is equal to n anyways for any lambda which is not in the spectrum of A. Moreover, note that because of the duality between controllability and observability, it suffices to prove only part A of the Hautus lemma. The proof of the Hautus lemma is split into two parts, one for necessity and one for sufficiency, where both of them will be proved by contraposition. First, for necessity, we start with the assumption that the system is not controllable. This implies that there must exist a block matrix A tilde 2 2 in the controllability decomposition, which has dimension greater than 0. So we can let lambda be an eigenvalue of A tilde 2 2 transpose with a corresponding eigenvector v tilde, and we can define the vector w tilde as the vector having zeros on top and then v tilde at the bottom. By the fact that the lower part of b tilde 2 is equal to 0, as we have seen before, it follows that b tilde transpose times w transpose is equal to 0. And similarly, by the fact that a tilde 2 1 is equal to 0, as we have seen before, it follows that w tilde is an eigenvector of a tilde transpose with corresponding eigenvalue lambda, meaning that lambda I minus a tilde transpose times w tilde is equal to 0. Therefore, with the definition of the vector w as t times w tilde, it's easy to verify that also b transpose w is equal to 0 and lambda I minus a transpose w is equal to 0. Hence, we have found a vector w in the null space of the transpose of this matrix, and therefore the rank of this matrix must be less than n. For the sufficiency part, assume that the rank of this matrix is less than n. Therefore, by theorem 6.9a, the null space of the transpose of this matrix cannot be trivial, meaning that there exists a non-zero vector v in Rn such that v transpose times lambda I minus a is equal to 0 and v transpose times b is equal to 0. Hence, by rewriting this equation, we have that v transpose a is equal to lambda times v transpose and v transpose b is equal to 0, which implies that v transpose times the controllability matrix P is equal to 0, which again implies that the null space of P transpose is non-trivial because we have found a non-zero vector v such that v transpose P is equal to 0 or P transpose v is equal to 0. And therefore, the rank of P is less than n, which means that the system is not controllable. Based on the Hautus lemma, we are now in a position to define and actually check the concept of stabilizability for linear systems. So, a continuous time or discrete time LTI system is called stabilizable if all eigenvalues associated with the uncontrollable modes are asymptotically stable, meaning strictly in the left half plane for continuous time systems or strictly inside the unit circle for discrete time systems. Now, a few remarks about stabilizability. First, clearly, controllability is a sufficient condition for stabilizability, meaning that a LTI system is stabilizable if it is controllable. And second, stabilizability can, in fact, be checked by using the so-called How-Tos test. And this How-Tos test works as follows. In the continuous time case, the pair AB is stabilizable if and only if for every eigenvalue lambda I, which is not asymptotically stable, we have that the rank of this matrix involving the eigenvalue lambda I must be equal to n. And analogously, for the discrete time case, the pair AB is stabilizable if and only if for every eigenvalue lambda I, which is not asymptotically stable, we must have that the rank of this matrix involving the eigenvalue lambda I is equal to n. And finally, for the sake of completeness, in corollary 13.36, we state that lambda is an eigenvalue of a tilde 2 if and only if this matrix becomes rank deficient if this value of lambda is substituted here. Now, pretty much the same process that we have just seen for the controllable subspace can also be followed for the unobservable subspace, where we again start with a discrete time linear time invariant system, and we call its unobservable subspace as UO. Again, the continuous time case is completely analogous and therefore omitted. By definition, any vector in SUO is unobservable as it has no effect on the outputs y of 0, y of 1 up to y of n minus 1, and in fact also not on the subsequent outputs. Recall from the proof of Theorem 13.17 that the unobservable subspace SUO equals to the null space of the observability matrix Q. So we can write SUO is equal to the null space of Q. Then we let Bn minus I plus 1 up to Bn be an orthonormal basis for SUO, where I denotes the nullity of the observability matrix Q, and clearly I is some integral number between 0 and n. And finally, we extend this basis by additional vectors b1 through bn minus I, for instance by using the Gram-Schmidt procedure. Then, as a result, we have expressed the unobservable subspace SUO as the span of the orthonormal vectors bn minus I plus 1 up to bn, and the orthogonal complement SUO perp as the span of the orthonormal vectors b1 through bn minus I. Obviously, SUO and SUO perp form a direct sum decomposition of the state space Rn. A similarity transformation, according to definition 12.1, with the transformation matrix T consisting of the basis vectors b1 through bn as columns, yields an equivalent system with the state x tilde being defined as T inverse x, and this similarity transformed system will be called the observability decomposition. Its system, input, output, and throughput matrix shall be denoted with A tilde, B tilde, C tilde, and D tilde in the following. Given that SUO is the unobservable subspace of the original system, we shall denote the unobservable subspace of the transformed system by SUO tilde, and it's given by this formula, which has a similar derivation to the formula for the reachable subspace in the case of controllability. Then we have lemma 13.38 stating that A, the subspace SUO, is A invariant, meaning that for any x in SUO, we have that also AX is an element of SUO, and B, the subspace SUO tilde, is A tilde invariant, meaning that whenever x tilde is in SUO tilde, also A tilde x tilde is an element of SUO tilde. Now to the proof of lemma 13.38. Part A will be again on exercise sheet 14, and for part B we will use the formula for SUO tilde that we have just obtained above. Now pick an arbitrary element x tilde of SUO tilde, meaning that T inverse x tilde is an element of SUO by the above formula, then it follows that A T inverse times x tilde is also an element of SUO by virtue of part A, and hence TA T inverse times x tilde is an element of SUO tilde by the above formula. Now all we need to do is notice that TA T inverse is equal to A tilde, and our proof is complete. In corollary 13.39, we now partition the matrix A tilde into 4 blocks, where the block A tilde 1 1 is an n minus I by n minus I matrix, and A tilde 2 2 is an I by I matrix. And the remaining 2 blocks, A tilde 1 2 and A tilde 2 1, have of course appropriate dimensions. Then the block A tilde 1 2 is equal to 0. To see why this is true, note that by the definition of T, the subspace SUO tilde consists of vectors of this form, where the first entries are 0 and the last I entries are non-zero. Hence, the result follows immediately with lemma 13.38b. Similarly, in corollary 13.40, we can partition C tilde into C tilde 1 and C tilde 2, where the dimensions of C tilde 1 and C tilde 2 correspond to those of the partitioning of the matrix A tilde. So C tilde 1 is a P by n minus I dimensional matrix, and C tilde 2 is a P by I dimensional matrix. Then C tilde 2 is equal to 0. Again, we just provide a short informal argument as a proof, and that's because SUO tilde is completely unobservable. Summarizing our findings, the observability decomposition can be expressed by this state space representation, where A tilde 1 2 is equal to 0 and C tilde 2 is equal to 0. The transformed state space model has the same input-output behavior as the original model, and the transformed state x tilde satisfies the usual relationship with the original state x, namely by x tilde is equal to T inverse times x. From this state space model, you can observe that the unobservable states never show up in the outputs, and they will never influence the observable states. Moreover, the eigenvalues of A tilde, which are the same as the eigenvalues of A, can be split into the eigenvalues of the submatrix A tilde 1 1 and those of the submatrix A tilde 2 2. The eigenvalues of A tilde 1 1 are also called the observable modes, and the eigenvalues of A tilde 2 2 are also called the unobservable modes. The danger here is of course that an eigenvalue of A tilde 2 2 is unstable, because then if the state blows up, this will never show up in the system output Y. Depending on the controllability of the pair A tilde 1 1 and B tilde 1, it may or may not be possible to control the system output. Finally, in the same way that stabilizability was a weakened concept of controllability, we now define detectability as a weakened concept of observability. In fact, a continuous time or discrete time LTI system is called detectable if all eigenvalues associated with the unobservable modes are asymptotically stable, meaning that they lie strictly in the left half plane in the case of a continuous time system, or strictly inside the unit circle for a discrete time system. Clearly, detectability is a weaker concept than observability, because every system that's observable will also be detectable, or phrased differently, a system is detectable if it is observable. For checking the detectability of a system, we can again use the How-Tos test, which in the continuous time case reads as follows. The pair CA is detectable if and only if for every eigenvalue lambda I, which is not asymptotically stable, we must have that the rank of this matrix, where we substitute lambda I here, is equal to n. And similarly, for the discrete time case, the pair CA is detectable if and only if for every eigenvalue lambda I that is not asymptotically stable, the rank of this matrix, where we substitute lambda I here, must have rank n. Now, on the final slide of this chapter, we have the Kalman decomposition theorem. The main idea behind this is as follows. So far in this chapter, we have decomposed the state once into a controllable state and an uncontrollable state. And then we have also decomposed the state into an observable state and an unobservable state. Now we bring both of these decompositions together and decompose the state into a controllable and observable state, a controllable and unobservable state, an uncontrollable and observable state, and an uncontrollable and unobservable state. And the Kalman decomposition theorem says that this is possible by choosing an appropriate change of coordinates, meaning an appropriate transformation matrix T. And if we do that, we obtain a system matrix A tilde, an input matrix B tilde, and an output matrix C tilde, which have zeros in the appropriate places. And moreover, the appropriate pairs A tilde 1, 1, B tilde 1 and A tilde 2, 2, B tilde 2 are controllable, and the appropriate pairs C tilde 1, A tilde 1, 1 and C tilde 3, A tilde 3, 3 are observable. So this theorem is a generalization of the controllability decomposition and the observability decomposition. It's kind of intuitive and the proof is omitted.